I give a quick introduction and then over to you. Yeah, so this is our third tutorial from Tom at Microsoft. Works on the Planetary Computer, doing lots of cool stuff, and yeah, I think he's going to take us through some of what Planetary Computer can do. I just clicked on this link, and yeah, I think Tom will take us through it. But it's an interactive session, so yeah, follow along. And over to you, Tom.
Awesome, thanks, Chris. Yeah, and definitely emphasis on interactive. So please, please, please do. I encourage you if you want to go through this. So in the chat here, I put the link to the hub where you'll be running your stuff at, where you can type in aka.ms/pc-cng, so Planetary Computer, Cloud Native Geospatial. That'll drop you into a JupyterHub instance where you can log in. Just pick a unique username, something that nobody else will pick. Don't know what'll happen if you clash there. I think you'll both end up in the same one, maybe in battle. I don't know. And then the password field will be geospatial. Yeah, so we'll wait a minute or so, let people get logged in. I can see see people showing up here in my little cluster. So I can briefly talk about what's going on in the background. So there's a JupyterHub deployment in Azure. If you're not familiar with JupyterHub, it's a way to do like multi-user Jupyter notebooks on various systems, and this one happens to be running on Kubernetes. So when you click that button, it starts up like a Kubernetes pod in Azure, which will be important, as we'll see in a second, and gets like the environment loaded up and the notebook server started up, and so you have compute next to the data. But we'll go into details there. I see people still showing up here. So I'll wait for just another minute. As we're waiting, yeah, go ahead, Chris.
It took me probably a couple of minutes. It like made some progress and then paused a bit, but I think it was probably 2 minutes.
I've tried to scale it up ahead of time, but we are hitting GitHub at some point to do like a Git pull. I'm very worried we'll get rate limited by GitHub. If only I knew someone there, but it'll be all right, I hope. Yeah, so it'll come up here hopefully, and then the first little bit here is mostly a little theoretical stuff, and then we'll get to some more hands-on stuff. I do have the chat open here on the side, so definitely post comments, questions, whatever. Let's keep it lively. That'd be more fun for everyone. I'm gonna make this a tad smaller. I'll post the link in the chat one more time. And if you have any troubles getting logged in, just post in the chat and we'll get you helped out. Okay. Just check in one thing. Okay, cool. All right, so yeah, Planetary Computer is the project that I work on with a few folks here at Microsoft. Gonna do like a very brief introduction to Planetary Computer, but the emphasis will be on like how the Planetary Computer is like taking a lot of these ideas from Cloud Native and kind of applying them to sustainability at scale. Oh, I should back up. If you've never used Jupyter before, Shift plus Enter is going to be your friend today. I think we'll have like a little exercise later on. But yeah, for now, Shift Enter is what's going to execute a cell. You can do fancier stuff like J and K to go up and down and insert new cells and delete them. But for the most part, Shift Enter will get you where you need to go. And if you've never used Python before, it'd actually probably be good, like if you want to put like your Python experience in the chat. I don't know, like these notebooks are for the most part filled out, and so don't get hung up too much on like the specific syntax or like how exactly do you do this in X-ray again or whatever, but I think the most value will be gained from like thinking about the concepts of like Cloud Native and how it maps onto this specific implementation. Jupyter works just fine with other kernels, R, you know, whatever. So we happen to be using Python today, just because that's what I'm most familiar with. Okay, back to the Planetary Computer. So we host a bunch of geospatial data on Azure. So you can go here for the catalog, which has a listing of all our data sets. So each of these is one or more STAC collections that have a whole bunch of data assets available for use to you. Just a couple of things to mention about like how we'll access that data in a minute. We'll get there in a second. I want to do like a very brief high level overview before we talk about accessing data. So we have a bunch of data in Azure that is there for people to use, ideally used from Azure. Getting all that data there into Azure is like a lot of work. It's not nothing, but it is, you know, well, you all know about STAC for the most part. So like, you know, that just having, you know, paths and blob storage is good, but not enough if you really want to do like geospatial data analysis. So we also have APIs. These are the docs for our STAC API here. Has search and all the stuff that you need there. We also have a data API, which we'll see in a bit, that has like, you know, some basic geospatial stuff that you might want to do built on top of T-Tyler. And then finally, we have a Dask-enabled JupyterHub. So right now, I don't want to like accidentally take down our Planetary Computer Hub. So we're on a different one. It seems to be holding up okay. If you're having trouble logging in, post it in the chat, but it seems to be working okay so far. So anyway, that's the basic idea behind the Planetary Computer is, you know, lots of geospatial data, APIs, and compute all on Azure. Okay, want to like get into, you know, list out these cloud native principles, you know, fundamental type things, and then we'll apply them in subsequent notebooks. First thing is that you have direct access to all of the data that we host. So it's like 30, 40 petabytes of data or something in Azure Blob Storage that you have access to. And like great thing about Blob Storage, it's, you know, nice and scalable. You can hit it in parallel from a whole bunch of machines, and lots of people can hit it in parallel from a whole bunch of machines. So it's just really necessary when you're hosting like these large of data sets that don't fit on a hard drive. These Blob Storage APIs are great. That clouds provide. So S3, Google Cloud Storage, Azure Blob Storage, Cloudflare has one, R2, I think. So yeah, lots of this Blob Storage API is very, very important for this. And in the case for the Planetary Computer is you just have direct access to the files in Blob Storage. So either using HTTP or like the Azure Blob Storage APIs to fetch the data. Wherever possible, we're using cloud native formats that we've been hearing about so much today. So COGS, R, GeoParquet, Copic, and wherever not possible or not done yet, we're experimenting with things like Kerchunk. So we'll see both of those in a sec. Next kind of high level principle, compute is next to data. We'll be talking a lot about this, but all of our data is in West Europe for best performance. Your compute should be in West Europe as well. And so that's where our compute is at here. And then finally, ability to scale. So, you know, it's fun to say like the cloud's infinitely scalable. It seems like this hub is holding up, scaling pretty well right now. I haven't seen any failed pods. So maybe it is infinitely scalable as long as you're not trying to use GPUs, maybe. Okay. Cool. So let's go through some of these. First one is like, I don't know, maybe the most important is like putting the compute next to the data. For performance, it can be super important, like latency, performance, throughput, things like that. I ran this command in my home internet in Des Moines, Iowa, just ran GDAL info on this cog in Azure Blob Storage. So returning like a few kilobytes of text maybe for the results. And it took 7 seconds. So that's like not great. We're now in Azure, run this and it's like 200 milliseconds, so 0.2 seconds. So I don't know, this is like a very simple and hopefully clear demonstration of why co-locating your compute with your data can be so important. You know, maybe in like the old way of doing things, you would start by downloading your data locally and then compute on it locally. And like that'd be fine because it's, you know, the compute and the data's co-located on your laptop or workstation. But if you're trying to work with like 40 petabytes of data, you know, that's not an option. You can't just download all of that data. So you do need to move the compute to the data, which can be a real challenge. And so we'll be talking through some of that, but yeah. Cool. And like I said, so we have the data there available for use. And then we also have APIs for working with that data, most notably the STAC API. Yeah, you're probably mostly familiar with STAC, but in case you're not, so we'll use this library, ADLFS, which gives you like a POSIX-like file system, os.path, whatever, API for working with blob storage. So there's S3FS for S3, GCSFS for Google Cloud Storage, lots of other ones. So like, I don't know if you know like how Sentinel names its files, but it's just like, there's all these letters, numbers, maybe a year in here. Hopefully that's like the year the image was captured. And if you're just trying to like figure this out, like where's March, you know, it's like, is that in a different path? So anyway, like the point is, if you're trying to just work with Azure, you know, blob storage, paths and blob storage to cogs, it's just like, I don't know, it requires either reading the docs, which you could probably do and figure that out, or you can just use STAC. So we'll use STAC here. We'll use PyStack client in this case, but great thing about STAC is it's standardized, so libraries like RStack or any of the other ones can work with the same STAC API. PyStack's just a convenient way to do it from Python. Connect to this catalog, and then we'll search for all of the Sentinel-2 images over Wyoming in 2020, July of 2021. And do that, and in a second or three, we get back our items. Okay, so 486 STAC items matched our spatial temporal query. Okay, you know, STAC, it's a standard. Great thing is like Landsat, we also have like Landsat collection 2, level 2, which has a completely different like naming structure. It's in a different storage account, container, bucket, if you're familiar with S3 or Google Cloud Storage. So it's completely separate. If you wanted to like do a similar sort of query just on blob storage, you'd like have to completely rewrite your code. But with STAC and the STAC API, we're able to just swap out the collection ID. So instead of Sentinel-2 L2A, we put Landsat 8 C2 L2, and we get back our Landsat items matching our query. Okay. One of the nice things about STAC items, GeoJSON features, so like STAC's all about metadata. We haven't actually loaded any cogs or anything yet, but we can, you know, load these up with libraries like GeoPandas and plot them on the map. So I don't know if this is meaningful or not, but you can kind of like plot the like acquisition path and date of each of these STAC items. They're over plotted on top of each other, but you can, you know, kind of get a feel for where your STAC items are at. Honestly, this is most helpful if you're trying to debug, like why is this item showing up in this query? Multiple times we found like, oh, your bounding box says you cover like all of this all the way down to Mexico, and it's like it should just be this little bit. So very helpful for debugging, but you can also do like analysis on these STAC items, and depending on the item, like it's got a lot of rich information there, things like the cloud cover and all sorts of rich information that can be actually analyzed on its own. So that is our STAC API, very briefly. We'll be using it a lot today. Briefly wanted to mention the data API. This is based on top of T-Tyler, which I think has been mentioned quite a bit already today. So yeah, we use it for several things. I'll show you in a sec, but in this case, we'll use the data API to plot an item. We make a plot of this Sentinel-2 item, and it's very, very cloudy, which gives an excuse to show off STAC's additional querying capabilities. you can query on anything within the item. So we'll query for, same query from Sentinel-2, Wyoming, July 2021, but we'll limit it to items that are less than 10% cloudy, as defined by Copernicus or whoever sets that. I'm not actually sure. We do that, and now we get our nice plot here on this map. And then since this is using T-Tyler in the background and like Folium or IPy leaflet on the front end, as we zoom in, we're going to get the higher resolution imagery returned by the tiler. And so this is all done dynamically and all that great stuff behind T-Tyler. I skipped over it kind of, but just to show like what we're doing is each of these items has a tiled JSON asset on it. So I'll pull out this first one. And if we look at that href, that gives a link to somewhere in the Planetary Computer with some parameters that I don't fully understand. But the upshot is if you make a request to that endpoint, you get back this payload, which tools like Leaflet and so on can know what to do with this URL to make stuff work that I don't understand, but is cool. Let's see. So Folium, I don't know the difference. I can try though. So like IPy leaflet. Leaflet's like the, okay, yeah, we're using IPy leaflet. Leaflet JS, like the JavaScript mapping library. IPy leaflet is a Python library built on top of it and IPy widgets, which are a way to get JavaScript interactivity into Jupyter notebooks using the Python kernel. Hopefully that was roughly correct. I'm not sure about the details, but that's the basic idea. And then as far as I understand, like that's what makes all this work. Like as you zoom in, it fires off things to like the bindings, IPy leaflet bindings. IPy leaflet calls into like leaflet JS or whatever, and it knows how to make the request to that tile endpoint. Roughly speaking, I think that's accurate. If anyone knows better about that whole chain, feel free to post that in the chat. Hopefully that's mostly correct. If you want, you can poke around at our Explorer. I would encourage you to do that. If you want to try and take it down by all browsing at the same time. Anyway, this is a way to, again, built on top of our STAC API and our data APIs, T-Tyler, to kind of bring this interactive visualization to these COG data sets. Last thing that we're not going to see today is scaling out on mini machines. But our JupyterHub for the Planetary Computer has this Dask gateway integration where you create a cluster, you scale it, connect to it, and then your computations that use Dask would be distributed on a cluster of machines. Okay, that's the introduction. And now let's get into the fun stuff. Over on the side here I'll try to slow down. Apologies. Items command I showed earlier. I'm not actually sure. I think I was, oh yeah, probably. I think just showing the Sentinel item 0. Sentinel item 0. Sentinel items, I don't know if I typoed that. But anyway, I think just showing the, here we go. Yeah, this one. It's just items. When you're ready to move on, we'll go to the data access notebook. Yeah, and in the chat, it looks like there's been some nice clarifications. It looks like IPy leaflet does kind of like bidirectional communication. Folium is just one way from Python to JavaScript. IPy leaflet goes both ways, it seems. Okay. I'm going to close this notebook, and you might want, also, it doesn't really matter for this one, you might want to restart it just to free up some memory. We didn't have too much data loaded there, but if you press 0 a whole bunch of times on that notebook, or I think you can, over on the sidebar here, on the stop, I guess is a top stop tab, you can shut down your running kernel, or I think in the file menu. So anyway, the next notebook we will open is data access. So you can click on the file widget here, and we'll go to data access. It's kind of fun notebook, fun for me. I don't know if it'll be interesting or not, but we're gonna these imports are just intimidating. It's a little odd, but we're going to load all of our types of data that we host in the Planetary Computer. So all sorts of different cloud optimized and not cloud optimized formats, all in one notebook. This will be fun. And they all start with STACs. So I'll give people a sec to get caught up here. We're moving on to data access. Okay. And yeah, if there are any questions, feel free to post them in the chat. I'm going to clear my outputs. I think they should be cleared in yours, but yeah. All right. Cool. So we're going to connect to the catalog again, and going to make a local Dask cluster. I might try to pull up this dashboard here. Two ways you can do it are click on this link, and it'll pop open a new window. I'm going to click on this Dask icon here, and I'm going to open up the, it pastes the URL here in the search box and press enter. I'm going to open up the progress in the task stream and lay them out here, just so we can see some stuff happening in the background as we're doing our computations. It'll take up a bit of screen space, but that's okay. Okay, so and just to note, this Dask cluster that we're using here is just on a single machine, which I think we have 4 cores. I can't remember what I ended up giving everybody, but I think we have four cores here. So we'll be processing in parallel on this single machine. The idea with Dask is, in the best case scenario, you're able to like swap out your cluster. Instead of a local cluster, you would have like a Kubernetes cluster, a gateway cluster, PBS cluster, or whatever you're using, and your computation would happen remotely. Okay. Just gonna catch up on chat here. Okay, awesome. Let's see here. Raster data. So the prototypical use case for STAC and cloud native geospatial stuff, I think. We're going to be working. Well, yeah, we have lots of different raster data. So Landsat, Sentinel, MAPE, Aster, all are like the remote sensing imagery data sets. Land use, land covers, like derived things, elevation things, variables like chorus, biomass, HGB, HREA is like electricity access. So lots and lots of different kind of cog-based data sets. Yeah, there's a question in the chat. I'm going to answer that in just a sec. So I'm going to go through this. Actually, yeah, I'll answer it here in a second. In this case, we're going to be accessing data from Sentinel-2 that is less than 25% cloudy over this bounding box. I can't remember. I think this is outside of Seattle. Yeah, so to answer the question in the chat, so when you're working with the Planetary Computer, these files themselves are in private blob storage containers. So you need to sign them, which kind of modifies the URL. It appends a little SAS token on the end of the URL that lets you actually read the data. And so the typical workflow when you're working with Dask, either on a single machine or a cluster, is to sign it locally, and then load the data using that signed URL. So just to show that, item square bracket 0.assets, I think B02 is an asset. That is the like actual path to blob storage, and my signed item will have this long SAS token appended to the end that actually lets you read it. Okay. So that's how you work with assets from the Planetary Computer, is sign it. All that's doing is making an API call to another API we run that hands out these SAS tokens. Okay. Yeah, and the question is, every access has a user assigned signature, so it depends. These are actually anonymous, so you can access all this data anonymously, which has some limits on like rate limiting for like how often we hand out SAS tokens, and that's maybe like the duration that the SAS token's valid for. Yeah, so you can do it anonymously, or you can include like a what do you call it? It's like a subscription key or an API key that has higher throughput and higher longer lived durations. in which case, yes, I think those, yeah, I'm not sure if those are logged or not at the user level. Well, let's see here. Yep, so we have our signed items there. And to go from a, lots of ways to go from a stack, collection of stack items that are somehow related to each other spatiotemporally. We're gonna use a library called STAC, which forms them into a data cube. There's also ODC stack, which came out of the Open Data Cube project, very similar idea. There's SITs from the R community, again, pretty similar idea of going from stack items to data cubes. So yeah, this is like a very natural two things coming together of this kind of stack metadata to form these nice regular data cubes. So here we have our stack data sets, our data cube as an X-array data array. I don't know if you've used X-array or not before, but if you haven't, it's kind of like NumPy array, so an n-dimensional array. In this case, we have time, so 36 time steps. Our band here, which is red and near infrared, we're going to calculate in DVI, and then our longitude and our latitude. Okay, so we have our four-dimensional array. The nice thing about X-array over something, it builds on top of NumPy and Dask, but the nice thing about X-array is you have like these coordinates, things like the time stamps for each one, band names, latitude, longitude in their native projection, things like that, and all the attributes that we get from STAC. So this is very, these go together very well. We'll go ahead and compute in DVI using the red and the near infrared bands, and we'll plot that on a map. This is using STAC. What it does is like, yeah, it's kind of doing something a little bit like T-Tyler on a Dask cluster. So the data is on the Dask cluster, and it's like doing the stuff to fetch specific tiles, and has like the we upsampled this, so it's coarse. It's fairly coarse, but it will adjust for that as you pan and zoom around. So it's like a quick little NDVI computation on this data. Okay, so that's COGS raster data. Earth systems data, which are typically stored as like ZAR or NetCDF. These might be like climate model outputs like TerraClimate, GridMet. CMIT SIPs downscaling things, reanalysis data sets like ERA5, observational data sets. I think iMerge is an observational data set, so lots of different kinds. We'll be working with TerraClimate using ZAR. This is stored as ZAR in Azure Blob Storage. One cool thing that you can do with STAC, it's very, very extensible. So we are implementing the X-array assets, I think is the name of the extension, on these assets. So if I open up that asset and convert it to a dictionary, you'll see things like these open quargs. And so what this is saying is, hey, if you open this asset with X-array, like you could open it with anything that reads ZAR, but if you open it with X-array, you should pass along these options like consolidated equal true. You might have like chunking information or things like that. So it's very nice to be able to go from, the only thing you need to know to access this data is the name of the collection and the name of the asset in this case, since it's a collection level asset. Okay. We get our metadata loaded for this data set, has a dozen or so different variables, all on the same grid here, time, longitude, latitude. We're going to, I think, select a single timestamp. If you haven't used X-array, apologies, but we're going to select a single timestamp here, the latest one. We'll grab the Tmax variable and then kind of make it a bit coarser just for the plotting. And then put that on a map. So able to quickly go from STAC to a visual of this data set. I haven't really talked about what's going on here. It's not super important, just looks cool. This is our cluster doing stuff. So like get item is like this thing, or maybe the selecting the time dimension. doing things like where and things like that. So you'll see stuff happening over here. This is like the activity of our cluster. This is one core over time. It's like reading data, doing stuff like this is probably the Corson mean or something. So not super important, mostly just looks cool. Yeah, this is the mean aggregation. So that'll just be happening over on the side, computing on this data in parallel. Kerchunk has come up several times today already. So just to show that in action, for this next GDDP CMIP6 dataset, that was distributed as netcdf files, a whole bunch of netcdf files, one per timestamp variable combination. So we have those netcdf files that you can just use if you want. It's just going to be a bit slow to access the metadata, thanks to how mostly how the metadata is written in the files. So what we've done is generated these Kerchunk index files and stored them as assets, in this case on the collection. We should have maybe done it as a separate collection. We might move to that in the future, but right now they're a collection level asset. And we can go ahead and, I'm a little hesitant to actually print this out. So it's like this 10 megabyte JSON file that I shouldn't print out. This refs, I think, is the large one. But anyway, the basic idea is this has all of the information that we need in this dictionary structure for kind of cloud optimized, efficient access to the metadata. This JSON file has a bit of metadata in it, things like the adders. I'll just load this up so we can see it. Things like the adders, but it doesn't have any actual data itself. The data, if we look at like one of these, this hers variable, that's still in the netcdf files. We haven't touched that. All that's in this references file is like the byte range that you would make. It has a URL to blob storage, and then the byte range request that you would make to get that subset of the data. So that's the basic idea behind Kerchunk, is store the metadata and these offsets in a JSON file, and then use a sophisticated client like FSpec's reference file system to load it up. And yeah, using the ZAR, it's compatible with ZAR, so we're able to load it up into Xarray. These ZAR files, the question in the chat, are the ZAR files downsampled for efficient loading of overviews? These ones are not. There is an emerging standard or two for like how you would represent that within a ZAR store. So there's a group of folks from like Carbon Plan who I think are talking tomorrow about how they're doing it for geodata. There's also people in the like biomedical imaging community who are using ZAR. They face a very similar problem as they want to like interactively work through this super high resolution imagery that comes off their microscopes. And they have another pyramid type specification for how to store those overviews, that equivalent of overviews within a ZAR group. So that's coming along, I would say. Moving along, that's ZAR or systems data. Operational forecast data, so we think like weather forecasts. We have some data. Our release was unfortunately delayed, so we're going to hit the staging API. Hopefully it stays up. This will be available in like a week or two through the regular Planetary Computer production API, but we're going to load up this ECMWF forecast data. This is a pretty complicated data set. There's like all different types of things, so we'll make extensive use of the query parameter to filter by these different attributes like the stream type and step. I'm not going to get into the details here, but if you've worked with this data before, you'll be familiar with it, and then check out the documentation for more details. These are stored as GRIB files, which unfortunately aren't the easiest to work with, with the whole cloud native, don't download the data, just stream it. So we're gonna, for now, download this, but we are experimenting with ways to fit this in with Kerchunk, and we have some prototypes that do that. But for now, we will download this file locally well, local to our remote kernel that's running in Azure. And then we have our data, again, as an X-array data array. So we've loaded up the metadata, not any data yet, and then do things like plot the significant wave height. Lots of quick little plots here that we'll put on a map. This is a global data set. I forget what the resolution is. So it takes a sec for the reproject. I think the reprojection is the slowest part, maybe. So while that's going, if there are any questions in the chat, I can answer them. But yeah, there's our nice, pretty plot of wave heights. To make a, I don't know, this is like fun stuff that you can do, like the joint distribution of the mean wave period along X and the significant wave height on Y. And like maybe that's meaningful to oceanographers. I'm not actually sure. I think it just looks cool. Okay. That is operational forecast data. Tabular data, carrying on. So in this case, we're gonna go through Apache Parquet and GeoParquet for the metadata. We're gonna be loading up the US Census data sets, okay? First one we'll do is on the congressional district level. That points to a file in Azure Blob Storage. So we'll go ahead and load that up using GeoPandas, but you can use any library that can read R. And we have our, I'll just show it over here, our geometry somewhere. I think I need to scroll over, but yeah, our geometry is over here at the end, and we can do things like use the Explorer to just quickly put that on a map for Maryland. Okay. For larger data sets, so Parquet has the idea of a data set. So that example used a file. It's a single Parquet file with all of the data. There's also the idea of a data set, which is basically like a folder of similarly structured data. In this case, we have a couple of those. One for the geometries, which has a bit of state FIPS code and things like that, and then the geometry. And then we have the population, which has, I think, this FIPS code here in the index, and then the geometries here. Sorry, the populations here. So no geometry, but we can do things like join those together. And since we're using Dask, this is all lazy, and we were careful about how the files were written. They were partitioned by state. And so we're able to, like, quickly, if you're doing some analysis that's either parallelizable across states, or if you only need to work with like a single state, you can do something like, give me, it's a little ugly, but anyway, give me, all the files for Rhode Island. So we'll use like the Panda style lookup by label here for these things that start with basically 4.4, and then load that up. And you can see that we only read, one chunk worth of data because all of Rhode Island is in a single partition. Okay, and we have all of our population data there. Oh yeah, I ran down the geometry. So anyway, same idea for the population. Okay. Cool. Point cloud data. Last one. We're almost there. This is a new one, but working with folks from Hobu to get this onto Azure. We're actually going to look at some LiDAR data from the USGS 3-depth LiDAR program over Chicago. Going to query for this area here. This is using the test API. This is really bleeding edge now, but it'll be available through staging and hopefully production soon, but I just kind of not include it. Again, using STAC to search for these Copic items that intersect with this geometry here, this circle. We can do stuff with PDAL that I do not understand, but you can ask Howard about that. Do things like we're going to create an intensity TIFF from the Copic file. And I think the thing to call out here is this execute streaming. So these nodes that we're on only have 8 gigs of memory. This Copic file is, I think, quite a bit larger than that. But we're able to stream in the chunks from blob storage directly into this PDAL pipeline without having to like load the whole thing or download the whole thing ahead of time. And we get out this TIFF at the end eventually. Okay. So that was a lot. But that's like, I think, unless I missed any, that's like all of the various types of geospatial data that we have in the Planetary Computer. So all in one notebook. Hopefully that was fun. Okay. And this will hopefully be a good reference. I should point out, I'll put this in the chat. If you're interested in the materials, they are here. Renee asked, the question is, was it decided how to pronounce Copic? I think they deliberately did not take a stance on that, unfortunately, but Copic, Copsy, whatever you want. Continuing the great tradition. So for this one, definitely do. We have loaded a lot of data. So, hit 0 a bunch of times, or file, kernel? Yeah, kernel, restart kernel. Definitely do want to restart your kernel here before we move on to this. I think if people want, you can choose. I have 2 more notebooks that we're not going to get to both of them. I think we'll move on to this Hurricane Florence animation just because it's, I don't know. But if you want, you can also check out the crop prediction example. But I'm going to go through Hurricane Florence. Okay. How are folks doing on like speed? Should I slow down? I definitely will slow down for this notebook, just because it's more, less like reference style. It's more analysis. So I'll slow down for this one. But if you do have any feedback, put it in the chat. Yeah, and it looks like I missed one question, but Alex was able to answer it. Typically, the question was like, if we have any examples, I'll put the docs here. Docs. I'll put the docs to where we describe that. This is specific for accessing data. Sorry, I think okay. Tokens for data access is what I'm looking for. This is for what we do on the Planetary Computer. But once you have a SaaS API, it applies for all of Azure. Once you have a SaaS token, it applies for all of Azure blob storage. Okay, let's dig into this one in our last little bit of time here. I'll play this just because it's fun to look at. I don't know if it shows up for you or not, but it's probably definitely not coming through the streaming software, but anyway, you can launch it there. So this is the thing that we'll be making. This might be a bit longer than what we do, but this is an animation of Hurricane Florence using imagery from the GOES satellite, which I think is just like, it's really remarkable, I think. Hopefully like scientifically useful as well. First thing that we need to do is figure out where on Earth the storm was and when. Okay. Fortunately, there's this really great data set. We don't have it in the Planetary Computer yet, but might want to do that. NCEI from the NOAA program is constantly updating this data set with a ton of information on storms of not just hurricanes. I think like lots and lots of different storms. If you look through I printed out DS here, this data set, and there's just so many data variables on each of these storms. It's just remarkable how much data is available for them. We're just going to be using a couple of bits of information, just the like the timestamp and the geometry, the latitude, longitude. Hurricane Florence had this storm ID. So we'll kind of look up by that. We'll select the data where the storm ID, SID, is equal to that storm ID, and then select out just the bit that we care about. Okay, we'll get and then build up this geometry thing, which we'll use in a second. Guillaume had a question about using the staging API in projects. Like, is it okay? Yeah, sure. It's a bit less stable than our production API. it will, in the future, like we don't guarantee like a link that works in staging today will work in the future, because we'll like recreate our staging database. So totally fine for using for like prototyping, experimenting stuff. But once it is available through production, you want to remove the dash staging. Okay. Now that we have the data just for this one storm, we're going to make a data frame, geodata frame, with the time and the geometry. We're also going to define kind of our endpoints. So we're not going to animate the entirety of the storm. We're just going to focus in on this one kind of day's worth of imagery. So you see the storm started, like, I don't know if they caught it immediately, maybe they go back and fill this in, but they have data on it from all the way here to when it makes landfall and eventually over the United States. So we're going to be animating this little bit here that's in red. Okay. All right. Yeah, so let's grab out the bounding box of our data set here. So this is just a list of latitudes and longitudes. And now we can actually use the STAC API to get the imagery. Okay, so again, connect using PyStack client in this case. The collection we're working with is the GOES CMI dataset. Using this bounding box and the date time endpoints that we defined earlier on, I can get rid of this limit. It's not necessary anymore, but you can leave it in, it doesn't hurt anything. And then we're going to use that query filter to limit the items to just those that are mesoscale. So if you, I should share this link, planetarycomputer.microsoft.com/catalog. For any of our data sets, you can go to the kind of detail page, get more information about that using things like the summaries. So in this case, there's the 3 image types here. There's an image capturing the continental United States, half the full disk of the Earth, and then mesoscale, which I think is like zoomed in on a specific region. And what's captured, I think, depends on the mode that like Modus or GOES is in. So I'm not quite sure how it works, but right now for this animation, we're just interested in this little bit, these mesoscale items. Okay. So these are, yeah, we can load up this first item here. I might make this, I'm going to close my Dask windows because we don't need them anymore. Make this a tad smaller, but we can load up this first asset and plot it and kind of get a sense for what the storm looks like for this one. And we're on, we definitely found it. So reversed here, this is water around the side, this is the storm here, but now we can go. So one thing about GOES is it's a geostationary orbit. It doesn't have a EPSG ID. So we can't use STAC. I haven't tried ODC STAC on this data set to see if it works with its GOES own CRS. But anyway, we're gonna just kind of do things the low level manual way right now, which takes a bit of time because we're actually opening up all the metadata, opening up all these files to read the geospatial metadata. But basic idea, we're gonna grab out the common names. So these are the names of the bands that we're going to be working with. We're going to get like blue, red, blue, and the other one near infrared. I can't remember what the band names are. And then we'll make a data array. We have our date times here that we can get from the STAC metadata. And then we have our collection of arrays here, one for each timestamp band combination. And we load that all up into a data array. So this is the kind of thing that STAC or ODC STAC does for you, and it does it faster. But end of the day, we get to the same thing as a data array with this kind of time band X, Y layout. Okay. Yeah, so next little step here. Oh no, I don't know if I, actually, maybe in the chat, do you have a like little prompt here? Maybe in yours, is this like green equal to, I can't remember if I pushed that change or not. This was supposed to be an exercise, but might have missed our chance for that. So anyway, I'll assume it's not an exercise because I think I have the latest version here. So apologies for that, but we're gonna do a bit of band math here to create this kind of fake green band because GOES doesn't have a true one. So we're gonna make it as a combination of the red, near infrared, and blue bands. So using X-rays, indexing here, and some math to get that green band. Okay. Now we can do some stuff that I found in some PDF somewhere about making the pictures look pretty. This gamma correctioning that I don't really understand, but we'll do that, and it does really make the image pop for sure. So that's our first image of the storm. Last little bit, not super relevant for cloud native geospatial, but is cool, is all the matplotlib stuff for plotting onto a figure. So gonna skip over this, but if you want to refer back to it later, you definitely can. We're just gonna go ahead and kick off that animation. You can see it run here, and it'll finish up in 30 or seconds, a minute or so. While we're waiting on that, if there are any questions, I'm happy to answer them. And we already saw the kind of original layout, the original animation earlier, but you'll be able to view your own animation, homegrown animation from your local, from your own Jupyter kernel. Yeah, hopefully that's satisfying.
Yeah, this is awesome. There was a question on, is it okay to use staging API in projects? What's the delay between staging to prod API?
Yeah, yep. So you can definitely use staging for like prototypey stuff. And then, it might break in the future. So don't rely on it for too long. Once it's available through production, definitely move to that. And then, yeah, as far as when it's available through production, we have like roughly quarterly releases. This one got delayed a bit, so it'll be end of April for stuff that's currently only available through staging, which we're very excited about. There's lots of new data sets coming up. Okay, that is Hurricane Florence. We have 7 minutes, so it absolutely does not make sense to go on to this next notebook, but I'll give like a high-level overview is using some label imagery from Radiant Earth's South Africa crop type competition, which have like a static stack catalog for, and then the kind of original imagery that was based off of from Sentinel-2 L2A, and kind of just going through an example of bringing together these two data sets, so the labels of like what is this field, what crop is growing on this field, and the actual imagery, and then training a little very basic machine learning model, a k-nearest neighbors model, to kind of try and predict the crop type based on the satellite imagery. I can't even remember, it's a handful of the Sentinel-2 bands. So that's like a fun little notebook for doing that. Use a STAC to do the querying and things like that. So I'll leave this up for a while longer. If you want to run through that notebook, you can definitely go ahead. Otherwise, and I'll put all this in the chat, the materials for today are here at this GitHub repository, Tom Augspurger / PCCNG Outreach 2022. And then I'll just drop a link to the planetary computer.microsoft.com, where you can go and learn about any planetary computer happenings. One thing I'll just explicitly note is like a lot of these examples that we did today came from just pulling data sets, examples from these notebooks. So each of our data sets has this kind of example notebook that gives like a very brief overview of that data set. So that is, I think, a pretty good place to stop for questions or a break or whatever. So yeah, if you have any questions, put them in the chat and I'll stick around to answer them.
Awesome, thanks so much, Tom. video on. We'll see if anybody drops them in the chat, and feel free to go. But yeah, I tweeted this. I love this tutorial because I don't know Python, but I can shift and feel like I'm doing stuff. Like,
yes, you're doing, yeah, for sure. Looks like there's a question about STAC or libraries. Yeah, when items cross the international date line, this has definitely been a challenge for us. I think we're still figuring out the best practices, but maybe you're supposed to like, yeah, I actually don't know, but we've done things where we, I think, split the geometry on the stack item to be a multi-polygon or something. I can't remember if that's the exact rule that what you're supposed to do, but yeah, it's been a challenge for sure.
Yeah, I kind of forget this too. I do feel like Stack's very GeoJSON based, and GeoJSON has at least a decent solution thought for this. So just kind of rely on what GeoJSON does for international date line.
Yeah, and we have not always done that. So if you spot any issues with any of our items, then definitely let us know and we can get them fixed. Question, do we have any roadmap for data sets? We don't have a public roadmap, but if there are Microsoft, we have this Planetary Computer GitHub repository that we just use for discussions. And if you go there, we've got a category topic, whatever they call it, for data requests. So if there's a data set that you want to see, you can go ahead and put them here. And then once once they're available, we'll go through and post here saying, hey, this is available now, and close them out. So yeah, that's a place to go. And when we add new data sets, we add them to our change log in our documentation. Another question, any timeline on when Sentinel-1 data will be available? I can tell you that Rob is working on that right now, this very second. So we have a GRD and RTC product coming online soon. Don't know exactly when that'll be. Hopefully very soon. Like in the next couple weeks, month or so. But yeah, we'll see. That's a big data set, so it could be a bit longer. Those files are actually available in blob storage already, just not available through the STAC API yet. Awesome.
Any other ones that you know are coming down the pipe soon?
Modus, that's very exciting. Yeah, it's really cool, and that one's especially cool. Looking at through the Explorer, it's really cool data set. Era 5. Part of Era 5. Yeah, decent chunk of data sets coming up in a couple weeks, hopefully.
Sweet, that's awesome. Cool, thanks so much for this talk, Tom. Super awesome. I think this will be a great one. I guess, yeah, one question, if people are watching this later, will they be able to log on, or is this a one-time?
Yeah, this link will go away. This aka.ms link will go away, but maybe I'll redirect it to the Planetary Computer .microsoft.com/account/request. And you can do once you sign up for an account and get approved, you can do very similar things on our hub. Yeah, so that's most likely future plans. That's the place to go.
Cool, sounds great. So future people that are watching this, do that.
Yeah, we tell you.